In this chapter, we derive the labor supply curve because workers supply their labor. And it all begins with the concept of utility and workers maximizing utility given their constraints. The first thing we're going to do is we're going to examine a utility function and understand how they work. Suppose the following function, and there's many functional forms you could use, but let's just use the following simple one. We have utility equal to the square root of consumption times leisure. Now, as I'm going to show you that the following function allows for diminishing marginal utility in consumption and leisure, which I think is important to understand. And the function also allows for consumers who get more consumption and more leisure, they're going to be generally happier. So that's what this following table does. So what we're going to do is we're going to plug 0 and 0 into the utility function. 0 times 0 is 0. The square root of 0 is 0. Next, we plug in $100 for consumption and 10 hours for leisure. Take the square root of their product is 31.6. Then we plug in 220. The square root of their product is 63.3. Plug in 330, their product, and then take the square root is 126.5. Then plug in $500 and 50 hours, take the square root, and you get 158.1. Notice that as both goods, as we consume more of both goods, we're generally happier and happier and happier. Now let's hold consumption constant at $300 per week. The more L goes up, the happier the worker is, but, so let's just check this for a second. 300 times 0 is 0. The square root of 0 is 0. Now, when we hold consumption constant at 300 and we increase L from 0 hours to 10 hours, our utility goes up to 54.8. If we plug in 320, our utility goes up to 77.5. It dropped, that change dropped quite a bit, right? When we go from 0 to 10 hours, utility goes up by about 55 hours. When we go from 10 hours to 20 hours of leisure, holding consumption constant, utility only goes up by about, 22 hours, or 22 utils. Then you plug in 30, plug in 40, you plug in 50. Utility is increasing, but at a decreasing rate. So marginal utility is the amount by which utility rises when the consumption of a good increases by 1 unit, holding all else constant. So using our same exact table, we're going to compute the change in utility, and we're going to compute the change in leisure. The change in leisure is 10 hours. We go from 0 to 10. The change in utility is 54.8 minus 0, which is 54.8. Taking that ratio, we get an average marginal utility from 0 to 10 hours of 5.48. So on average, from 0 to 10 hours, when leisure goes up by an hour, our utility goes up by 5.48 utils. Okay? Then, if we go from 10 hours to 20 hours of leisure, leisure goes up by 10 hours. Utility goes up by 77.5 minus 54.8 for an increase in leisure of 22.7. So the average marginal utility from 10 to 20 hours is 22.7 divided by 10, which is 2.27. So on average, when we're going from 10 hours to 20 hours of leisure, an additional hour of leisure means our utility only goes up by 2.27. So marginal utility is diminishing as leisure goes up. Then we have an increase in leisure of 10 hours again. Utility increases by 17.1 utils. So on average, between 20 and 30 hours of leisure, an additional hour of leisure will yield 1.71 more utils of utility. 10 hours of leisure, additional hours of leisure, yields us 14.6 additional utils. On average, increasing leisure by 1 hour increases utility by 1.46. Increasing utility by 10 more hours increases utility now only by 13. On average, if we increase leisure by an hour, we're going to see our utility increase by only 1.3 utils. Now let's look at indifference curves. Again, we're using the same exact utility function, U equal the square root of C times L. If the worker is indifferent between all market baskets located on an indifference curve, then U is being held constant along it while L and C change. Leisure and consumption change. Now, let's just assume utility is some given number. It might be 100. It might be 1,000. So rather than plugging in a number, we're going to hold it constant. We'll make it red and give it a subscript 0. So it's given. It's known, period. Whether it be 100 or whatever. So because consumption is on the y-axis and leisure is on the x-axis, we're going to solve for consumption. So all we do is we square both sides of this equation, right? That gets rid of the root on the right-hand side. Then we say utility squared equals consumption times leisure. Well, that's the same as saying consumption times leisure is the same as utility squared. Now all we got to do is divide by leisure. As long as leisure is not 0, which I don't think it is for anybody. As long as leisure is not 0, we can divide both sides by L. And this is the equation for the indifference curve, given a utility level of U0, whatever U0 happens to be. So let's do an example. Suppose utility is 10. We'll hold utility constant at 10. Plug 10 in for U0 and you get 10 squared. 10 squared is 100. So let's graph the indifference curve, holding utility constant at 10. Here's a table. If leisure is 10, 100 divided by 10 corresponds to a consumption level of 10. Plot that point. So here leisure is 10, consumption's 10. Okay, let's plug in 40. 100 divided by 40 is 2.5. So when leisure is 40, consumption is 2.5. Let's plug in 100. When leisure is 100, 100 divided by 100 leaves us with a consumption level of 1. So when consumption is 100, leisure is 1. Now the curve, the smooth curve that connects these dots, is the indifference curve with utility equal to 10. Now what happens if utility rises to 20? Replace U0 with 20. 20 squared is 400. 400 divided by L is the equation for the indifference curve when utility is 20. Let's graph it again. When we plug in 10, we get a consumption level of 40. So when consumption is 10, well, 40 doesn't show up on the graph because the highest C can get here is 15. So it's way up here. The point's way up here. Okay. Now when we plug in 40 for leisure, consumption is 10. So 40 for leisure, 10 for consumption. And remember, this other point's way up here. Then we plug in 100 and we get a consumption level of 4. So when leisure is 100, consumption is 4. Now we connect the dots with a smooth curve. And we label that curve utility equal to 20. So indifference curves in labor economics are bowed toward the origin. They don't curve in, and they don't curve up, and they don't intersect. And everywhere along an indifference curve represents the same level of utility. Now, when you move from one indifference curve that's close to the origin to one that's away from the origin, utility goes up. Now let's look at the budget line. This says consumption equals the wage times hours worked plus an allowance. Now that allowance might come from your mom. If you're going to college, she might give you $100 a week. So you don't have to work because she wants you to focus on getting good grades. If you're an adult with maybe 2 or 3 kids, the allowance might be a TANF payment, a welfare payment. So we're just going to call it A for allowance. It could be an actual allowance or it could be a payment from government. Now, this is our time constraint. This is our budget constraint, and this is our time constraint. This says our total time each week equals how much leisure we want to do plus how many hours of work we want to do. L could be L could be interpreted as household production, taking care of your kids, doing dishes, teaching your kids how to read, right? If you work a lot, then you have to pay somebody to do that stuff for you. So leisure is kind of a term that has a negative connotation. You can think of it as household production. Now, all I did here is I subtracted L from both sides, and H equals T minus L. So as H goes up, leisure must be going down because the total time available in a week is known. You got 24 hours a day, 7 days a week. That's a fixed amount of time. So if you're working more, you're leisuring less. Now all I did here is I took the H and I replaced it with what H equals, T minus L. So this is just W, wage, times hours worked plus an allowance that you might get from your mom or your dad. Or you might get it from government. Now C and L are the variables of interest here. C is on the y-axis and L is on the horizontal axis, and everything else is known. Constraints set boundaries on a worker's opportunity set of all the consumption baskets the worker can afford. Here's an example. Suppose you will at most work 80 hours a week, which I think is reasonable because that's about 2 jobs. And if you're a small business owner, you're probably working 80 hours a week. Now, my dad would work 120 hours a week on his farm before my parents got divorced, which probably explains one of the reasons why they got divorced. Now, the allowance is $100 here, so maybe government is giving you a $100 a week allowance, which would be about $450 a month in a welfare check. And maybe you can make $10 an hour after tax. So this is your net wage. So here's the consumption line, or the consumption equation. This is 10, that is 80, that's 100, and that is 10. Plug in the numbers. Notice we didn't plug in for anything for L or C. We don't plug in anything for L or C until we get ready to graph it. 10 times 80 is 800. 800 plus 100 is 900. This right here is our budget line. Okay, so let's graph it. If we have 10 hours of leisure, 10 times 10 is 100. 900 minus 100 is 800. So when leisure is 10 hours, consumption is 800. Plugging in 40 into the budget line, we get 500. Why is that? 10 times 40 is 400. 900 minus 40 is 500. Another way to think about this is you have the $100 allowance, right? And if you have 80 hours a week and you're leisuring for 40, that means you're working for 40. So 40 times 10 is 400. 400 plus 100 is 500. So either way, you get $500 of consumption. So when leisure's 40, consumption is 500. When you plug in 80, 80 times 10 is 800. 800 subtracted from 900 is 100. Now, another way to think about this is if you're leisuring for 80 hours a week, you have no time to work. So 0 times 10 is 0, and 0 plus 100 is 100. So when leisure is 80, consumption is 100. You're consuming your allowance. The budget line connects the dots. It stops at 80 because, remember, you don't have any more time than 80. 80 is the maximum amount of time you can devote to hours worked or leisure. What happens if A increases to $200 per week? Well, let's just go back to our equation. C equals W times T plus A minus WL. Now we're holding everything else constant. So the wage is still $10 an hour. Your time available for work and leisure is 80 hours. But your allowance increased to 200. So your budget constraint becomes what? It's 1,000 minus 10L, which makes sense because instead of having a $100 allowance, you have a $200 a week allowance. So let's fill out the table again. When leisure is 10, consumption is 900. 1,000 minus 100 is 900. When leisure is 40, 1,000 minus 10 times 40 is 600. When leisure is 80, well, 80 times 10 is 800. 1,000 minus 800 is 200. So the budget line shifts up. It's a parallel shift up, and it shifts up by $100. Let's scratch that last increase. Suppose instead the wage increases to $12 per hour. So holding everything else constant, T at 80, allowance at its original value of 100, what happens to the budget line? Well, let's ask the question, what happened to W times T? 12 times 80 is 960. The allowance is still 100, and the wage is 12. So both the slope and the intercept rise in this case. Okay, so let's fill out the table again. 10 times 12 is 120. 120 subtracted from 1060 is 940. 12 times 40 minus, or subtracting that from 1060 gives you 580. 80 times 12 and then subtracting that from 1060 gives you 100, which makes sense, right? Because if you leisure all the time, you're not working in the labor market, you're not making any money in the labor market, you can only consume your allowance. So the budget line rotates. Notice that the intercept increased and the slope increased. Intercept increased and the line got steeper. Just the opposite is true if wages fall. Individuals will choose consumption and leisure to maximize utility. Optimal consumption is given by the point where the budget line is just tangent to the indifference curve. At this point, the marginal rate of substitution between consumption and leisure, that's the slope of the indifference curve, just equals the wage rate, the slope of the budget constraint. Any other bundle of consumption and leisure given the budget constraint means the individual would have less utility. Example, all right, the budget constraint with T equal 80 hours per week, an allowance of $100 per week, and a wage of $10 per hour gives us the budget constraint below, which we already graphed in a previous slide. Now, suppose utility is U2. No consumption bundle on U2 can be achieved or reached by this consumer because they are limited to consumption bundles along the budget line. Remember, there is no saving in this household. We're assuming there's no saving. All income is consumed. Indifference curve U0 intersects the budget constraint twice, once here and another time here. All of these points that are inside the budget constraint are attainable. The points on the budget constraint are attainable. But remember, in our model, the consumer doesn't save. So the consumer would either be at this point or at that point. Now the marginal rate of substitution is the slope of the indifference curve. The slope of the indifference curve at this point is pretty small relative to the slope of the budget line. The slope of the indifference curve at this point, the marginal rate of substitution, is really, really large compared to the slope of the budget line. So at neither one of these points does the marginal rate of substitution equal the slope of the budget line, the wage. The indifference curve that corresponds to U1 is just tangent to the budget line. It just barely kisses it. It only touches the budget line once at the tangency point. This is why I say that the marginal rate of substitution, the slope of the indifference curve, is equal to the slope of the budget constraint, the wage, at the optimal solution. Now the optimal solution here is leisure is 41, therefore hours worked would be 39. Consumption is 490. We plug leisure into the consumption equation and we get 490. 10 times 41, subtract that from 900 is 490. Another way to think about it is, since hours worked is 39, 39 times 10 is 390. 390 plus the allowance is 490. So either way you do it, you get 490. So what happens if the allowance increases to $200? Well, remember previously from a previous slide, the budget constraint shifts up in a parallel direction. The intercept increases from 900 to 1,000. Now, the optimal solution is somewhere between here and here. The new optimal solution can't be on this side or that side because that would imply the indifference curves intersect, and they can't. So the indifference curve, the new indifference curve comes in here, is tangent to this red line anywhere inside this indifference curve U1. Now here, in this particular example, yields an optimal solution where leisure is 38. Now leisure is an inferior good here since hours of leisure falls as the worker's income increases to $200. Now with leisure equal to 38, that means consumption at this new optimal point, optimal solution, is $620. Hours worked, it would be 42. Well, let's look at a different individual. Maybe a different individual responds to an increase in the allowance of $200 differently. This particular individual does what? Well, their optimal solution is leisure equal to 50. Here, leisure is a normal good since hours of leisure increases when the allowance increases or income increases. Consumption would be 500 and hours of work would be 30. So this particular individual will work fewer hours. They go from 39 hours of work down to 30 when their allowance goes up. Now each one of you doing this on an exam would get different numbers because you're all going to draw this indifference curve on different parts of the new budget line. And where you draw it is up to you. As long as the optimal solution is somewhere on the inside part of the budget constraint, inside U1. Now what happens if the wage increases to $12? Remember, the wage increases to $12 because the old wage was $10 and the wage enters the intercept and is the slope. Both the slope and the intercept increase. So the budget line will rotate clockwise. And at this point, again, the indifference curve could be tangent, the new one could be tangent to this part of the budget line down to this part of the budget line. It just depends on where you draw it. Suppose I put it right here. What does that say? Well, leisure is now 40 hours per week. Now, since W is the price of leisure, the law of demand holds, right? Because leisure went from 41 down to 40 when its price increased from $10 to $12. Now plugging the 40 into our consumption equation, we get 580. So at this point, the worker is working 40 hours a week, leisuring 40 hours a week, and is consuming $580 worth of goods per week. An increase in W, the wage, increases H because the substitution effect dominates the income effect. And we'll do more on this later. What happens if W increases to 12 and we have a different individual? Again, the budget constraint rotates clockwise. And again, you can draw the new indifference curve anywhere along the budget line inside this indifference curve. This time I drew it down here. And it looks like leisure is about 46 hours. Consumption would be 508. And hours worked would be 34. So this person, when the wage went up, this person actually worked less. They went from 39 hours of work each week to 34 hours of work each week. And why is that? Well, the income effect dominates the substitution effect. And we're going to graph this again in the future. So here it goes. When the income effect dominates, now when you're decomposing substitution effects and income effects, what you do is you start at the original budget line. The black line is the original budget line. Going from black to red suggests that the wage is increasing. So what you do is you shift the black line up until it's just parallel to the new indifference curve. And we call this blue line the hypothetical budget line. And we call this point here the hypothetical optimal solution. Okay? So the income effect is from 40 to 60 hours. And the way you think about that is, remember, a parallel shift of the budget line means income, non-earned income, the allowance rose, and the wage was held constant. So the way you think about the income effect is, if you want the worker to be indifferent after the change, indifferent between an increase in a wage and just be given an allowance, the amount of money that the person has to be given is this height. So this height here, from this point down to that point, is how much money this worker would need to be given that is independent of the wage in order for them to be indifferent between that sum of money and an increase in the wage. That's why I call it the income effect. The substitution effect is the movement along the new indifference curve. The movement along the indifference curve from the hypothetical optimal solution to the final optimal solution. That's the substitution effect. And notice the income effect is bigger than the substitution effect. So the total effect is from original optimal solution to final optimal solution. An increase in W here decreases H because the income effect dominates the substitution effect. Remember, when you go from black to red, the wage is increasing. And since leisure is increasing, hours worked decreases. Now, when the substitution effect dominates, we again move from the original budget line to the new indifference curve. So this height here, from here down to here, is the amount of income that the worker would need to be indifferent between that amount of money and the increase in the wage. That's why we call it the income effect. The substitution effect, again, is the movement from the hypothetical optimal solution to the final optimal solution. And notice the movement is along the indifference curve. We're keeping utility constant from this point to that point. And as we move from this point to that point, leisure is falling, consumer consumption is rising. So we're willing to trade leisure for more consumer goods on the substitution effect. That's why we call it the substitution effect. And here the substitution effect dominates the income effect. So leisure falls, hours worked increases when wages go up. So in summary, an increase in the wage increases hours worked because the substitution effect dominates the income effect. Now the reservation wage, it's essentially the wage that you would need to go from not working to working the first hour in a given week. Okay, if the market wage is less than your reservation wage, say you're only going to be paid $3, say the market wage is $3 an hour. I doubt anybody listening to this video would want to work for $3 an hour. Now, as that wage comes up, maybe it goes to $5 an hour. Well, one person out there, like a young kid, might want to work for $5 an hour. So that young kid's reservation wage is $5. If that wage continues to rise to, say, $6, well, then more people are going to want to work. So the people that decide to work when the wage gets to $6 would have a reservation wage of $6. Now, most students are looking to graduate and get a really good job. So I doubt very many students would leave school to make $15 an hour. You may want to work a job where you're making $50 an hour and go to school at the same time. The reservation wage increases as non-labor income increases. If you're getting $0 from your mom and you want to hang out with your friends at the movies, well then, in order to do that, you might have to work a minimum wage job. But if your mom's giving you $500 a week, there's no reason for you to find a job because you have enough money to cover your expenses while you hang out with your friends. So it makes sense. The reservation wage increases as non-labor income increases. In the diagram below, this particular worker is not working at all. Notice how flat the budget line is. It's really, really flat. So the wage is really, really low here. So this worker chooses not to work. This worker is leisuring 80 hours a week and not working at all. So what is this person's reservation wage? Well, it's not the slope of this line. Okay? The reason why this person doesn't work, if this person was working, say 40 hours a week, which point makes them more happy? This point or that point? Well, remember, indifference curves that are closer to the origin represents lower levels of utility. So this person is not going to work 40 hours a week. They'd rather work nothing each week, leisure for 80, and collect that allowance. So if W increases a little bit, say that amount. Now if you look at this budget line here, this budget line is tangent to the indifference curve. This line here isn't tangent because if you extend it, it'll be out here. But if you extend this red line, it will not cross the indifference curve. Okay? So with this red wage, if the wage is equal to the slope of this red line, the worker, you can think of it this way, the worker is indifferent between working and not working. Okay? So in order to get this person to work, you'd have to give them maybe a penny more per hour than the wage that is on that red budget line. Because as soon as you raise the wage on that red budget line to a wage like that amount, this wage is really large. Now the person starts working. This person begins working 10 hours a week. Okay? So the slope of the indifference curve that passes through the endowment point right here, we call that the endowment point because each person is endowed with 80 hours that he or she can use for work or leisure and an allowance of $80. So we call that the endowment point. So the reservation wage is equal to the slope of the indifference curve that passes through the endowment point. Not the budget line that passes through the endowment point, but the slope of the indifference curve that passes through the endowment point. Okay, so at this new W, this new higher W, the leisure is 70, hours worked is 10. Okay, the relationship between hours worked and the wage rate is the labor supply curve. At wages slightly above the reservation wage, the labor supply curve is positively sloped because the substitution effect dominates the income effect. If the income effect begins to dominate, hours of work will decline as wage rates increase. So we say the labor supply curve bends backwards. Labor supply elasticity is equal to the percent change in hours worked over the percent change in the wage rate. Labor elasticity less than 1 means inelastic, or you're insensitive to a change in wages. Labor elasticity greater than 1 means labor supply is elastic, or you're very sensitive to a change in wages. Here's an example of a backward bending labor supply curve. Now, when the wage is $10, this person works 24 hours a week. If the wage increases to $20 an hour, this person will work 40 hours a week. The substitution effect dominates the income effect here because why? Hours of work is going up in the total effect because the wage went up. The elasticity here is the percent change in hours worked divided by the percent change in the wage. Well, we're going from $10 an hour and 24 hours of work to 40 hours of work because the wage increased to $20 an hour. So this down here is the percent change in the wage, and this down here is the percent change in hours worked. Final minus initial divided by initial. Final minus initial divided by initial. Or what are the hours worked minus what were they divided by what were they. What is the wage minus what it was divided by what it was. Okay, so if you compute the elasticity, you get a 0.667. Okay, we're inside of -1 and 1, so we say labor supply is relatively inelastic when you go from this point to that point. Now notice right here, if you were to zoom in on this point here, the labor supply curve would look very vertical, right? At that point, you could say that a very, very small increase in the wage would do nothing to hours worked. So at that point there, labor supply is at its greatest level of inelasticity. Now suppose the wage increases by $7. So your hours worked would fall from 40 to 30. And that's because your income effect dominates your substitution effect. Because remember, hours worked is falling when the wage goes up in the total effect. That's because the income effect is now dominating the substitution effect. So you compute the elasticity. Remember, this is where we start, a wage of 20, 40 hours of work. This is the new wage, and this corresponds to hours worked at that new wage. What is hours worked? 30. What was it? 40. What was it? 40. What is the wage? 27. What was it? 20. What was it? 20. So elasticity here is negative 0.71. Again, this is inside the -1, 1 interval. So we say that labor supply is inelastic. Okay. Down here, the elasticity is positive. Up here, the elasticity is negative. The elasticity up here is negative because the income effect dominates the substitution effect. The elasticity down here is positive because the substitution effect dominates the income effect. Now, this is the percent change in the wage, and this is the growth rate of female labor force participation. Now we fit a regression line to this scatter plot, which reveals a positive relationship between the percent change in the wage and the growth rate of female participation in the labor markets. When the percent change in the wage is 2%, the female labor force participation rate only grows at about 1.25%. If the wage for women in the labor market is growing at 8%, the labor force grows by about 4.75%. So beta hat here, the estimated slope of this regression line, would be about 4.75 minus 1.25 divided by 8 minus 2, or 3.5 divided by 6, or 0.583. Thus, this line is suggesting that the substitution effect dominates the income effect for women in these labor markets between the years 1960 and 1980. Now, we've already looked at what happens if government simply transfers money to low-income single mothers. Their budget line will shift in a parallel fashion outward. Now, before welfare reform, the more somebody worked, the more their benefits were reduced. And what officials found is that this reduced work effort, which made women more dependent. So this is kind of how welfare worked before the reforms of 1996. Now, if your allowance is, if the welfare check is $5 per month, and the person is making $5 after tax, and the benefit reduction rate is 50%, then this table illustrates the effect on a low-income mother's budget line. Now, the benefit reduction rate works this way. If your earnings go up by $1, your benefit's going to go down by 50 cents. So it's kind of like a tax. I'm going to show you with this example. Now, when you're making $5 an hour, but you don't work at all, your earnings are $0. Your allowance is $500, and since you didn't make any money, your benefit, the $500, is not reduced by anything. So your actual transfer is $500. This is what you'd actually receive in the mail from government, and then your total income for the month would be $500. Now, if you work that first hour, 1 times 5 is 5, so your earnings would only be $5 a month. If you worked 2 hours in a month, then your earnings would be $10. If you worked 3 hours a month, then your earnings would be $15. If you worked 176, your earnings would be $880. If you worked 199 hours a month, your earnings would be $995. 200, $1,000, 201, $1,005. 202 hours in a month, $1,010. Notice every time it goes up by $5. Now your allowance, if your allowance would be $500, no matter what your earnings would be, if government didn't reduce your benefit by 50 cents for every dollar of earnings you increase your earnings by. But before welfare reform, government typically penalized you for working an extra hour in a month. So if the benefit reduction rate is negative 0.5, then because you made $5 by working that 1 hour, your benefit of $500 is reduced by half your earnings, which is 5. 5 times 0.5 is 2.5. Now, if your earnings are $10 per month, your benefit check would be reduced by $5, half the 10. If your earnings for the month were $15, your benefit check would be reduced by $7.50. If your earnings are $880 for the month, half that's $440, so your benefit would be reduced by $440. If your earnings are $995 for the month, half of $995 is $497.5, then your benefit would be reduced to $497.50. If your earnings are $1,000, then your benefit is reduced by $500. Now, at this point, you're not getting anything from government. The government would give you $500 if you didn't work, but because you're making $1,000 a month, the government takes away $500. So from this point on, government is essentially taking away your benefit check. So you're getting a net from government of $0 for all earnings greater than 1,000. So your actual transfer is 500 minus 0 if you work 0 hours. It's 500 minus 250 if you work 1 hour. It's 500 minus 5, or 495, if you work 2 hours. It's 500 minus 7.5, or 492.5, $492.50. It's 500 minus 440, or $60, if you work 176 hours in a month. It's only $2.50 if you work 199 and make $995, and then your actual transfer is 0 thereafter. So your total income when you worked 0 hours is 500. When you work that 1 hour, your total income is 497.5 plus 5. When you work that 2 hours, your total income is your actual transfer, 492.5, or 495 plus 10, or 505. If you work 3 hours in the month, your total income is your actual transfer, the check you get from government, 492.5 plus 15. If you worked 176 hours, your earnings would be 880. Your actual transfer would be 60. So your total income would be 940. If you worked 199 hours in a month, your earnings would be 95. your actual transfer from government would only be $2.50, and your total income would be $997.5. From that point on, your total income is just your earnings. Okay. Now notice this difference here. Working that extra hour means your wage, your kind of your net wage after the benefit reduction rate is only $250. This difference is $250. This difference is $250. This difference is $250. So for all income levels, total income levels, from 0 hours of work all the way up to 200 hours of work, your income is only going up by $2.50 for every additional hour you work. So the benefit reduction rate acts as a tax. And anytime you tax something, you get less of it. So because we're taxing essentially labor here, this has a tendency to reduce low-income single mothers' employment effort. In the following diagram, we're going to demonstrate how a benefit reduction rate acts as a tax in reducing low-income single mothers' employment. Now, in the diagram below, the employee is working 100 hours a month because their leisure is 100 hours a month. 100 times 5 is $500 in earnings. This is before they sign up for welfare payments. If they sign up for welfare payments and they don't work at all, they'll get a $500 allowance. Now, I demonstrated in the previous table that the 50% benefit reduction rate acts as a tax on earnings because for every dollar your earnings increase by, your benefit of $500 is reduced by half a dollar. So we have this red budget line that has a slope of 250. The black line has a slope of 5. Recall in the previous table when hours worked got to 200 hours, the worker made $1,000 in a month. And with a benefit reduction rate of 50%, 50% of 1,000 is 500. So taking the $500 from the monthly benefit meant from that point on, the person didn't receive any money from government. So for that reason, this part of the red line disappears. Given this budget constraint, a low-income single mother might end up working 100 hours. This person is choosing 150 hours of leisure if this person has 250 hours total in a month to split between leisure and work. Now let's compare that to a scenario where states choose a benefit reduction rate equal to 100%. In this scenario, workers will not work because earnings are taxed at a rate of 100%. Let's compare this to the previous. A benefit reduction rate means the budget line rotates until it has zero slope, resulting in the woman being made worse off. Remember, the woman was on U1 when the benefit reduction rate was 50%. Now the woman is on a difference curve, the indifference curve that's between U0 and U1. So her utility is lower, and this woman works 0 hours a week because her leisure is 250 hours a month. Now let's compare that to a benefit reduction rate of 0%. This is the scenario that we modeled very early in this lecture handout when we had a parallel shift in the budget line. So with a benefit reduction rate of 0%, the budget line is a parallel shift up. This results in higher worker utility, and this particular worker works 130 hours per week. Recall that the same worker, if faced with a 50% benefit reduction rate, would only work 100 hours. Hence, reducing the benefit reduction rate from 50% to 0% raises hours worked from 100 hours to 130 hours. Because lowering the benefit reduction rate from 50% to 0% increased work effort, policymakers in the early 90s went a step further. They, instead of going to 0, they went to a negative 0.4, or what we call a wage subsidy. A wage subsidy is the opposite of a tax on wages. And this program is called the Earned Income Tax Credit. This part of the red budget line, the Earned Income Tax Credit budget line, from here down to here is where the wage subsidy kicks in, the 40% wage subsidy. We call this the phase-in region. And there's a region where it acts like a transfer, a parallel shift in the budget line. The phase-out region is not shown in this diagram. The phase-out region is a flattening of this red Earned Income Tax Credit line. Recall that when the benefit reduction rate was 50%, this indifference curve here represented the maximum amount of utility the consumer had when the benefit reduction rate was 50%. And that worker worked 100 hours a week. But with this wage subsidy of 40%, the worker now works 170 hours a week. Thus, the Earned Income Tax Credit program can really incentivize low-income single mothers to work much, much harder. As I had mentioned earlier, the previous slide does not model the entirety of the Earned Income Tax Credit program. The way it works is you have this budget line of a person that is not applying for the Earned Income Tax Credit, which is part of your annual tax return. So if you don't apply for the Earned Income Tax Credit, this is what your budget line would look like. If you apply for the Earned Income Tax Credit program via your tax return, then the budget constraint, the Earned Income Tax Credit budget constraint, is steeper than if you don't apply for the Earned Income Tax Credit. The net wage is 40% above the actual wage. And that continues up until you get to income levels of $14,490. From $14,490 up to $17,660, the net wage equals the actual wage. So essentially what's going on here is the government's just giving you a straight up transfer. Then from $17,660 until your income gets to $33,178, the Earned Income Tax Credit program works as kind of like a benefit reduction rate. It taxes your earnings. So the net wage is 21.06 below the actual wage. Now beyond $33,178, the net wage equals the actual wage because you're no longer eligible for any Earned Income Tax Credit funds. And what this program is intended to do, it's intended to kink your budget line so that you go from working very little to working more hours per year. Next, we're going to look at the firm's problem. Firms maximize profits. The result of maximizing profits is what we call the labor demand equation.